We're going to continue our discussion, and then here we want to look into Voronoi diagram, right? So what did I call it? I said Voronoi in between. Yeah. Are you annoyed? Anyway, see, it's Voronoi diagram, right? So it's kind of simply a kind of a polyhedron, some shape that shows you the instant space. You studied the concept of version space in your ID3 algorithm, right? Yes? Not ID3, please. Your candidate elimination. Yes, in the candidate elimination, you studied the concept of your version space. So this instant space is called the Voronoi diagram. It's just kind of a polyhedron. And you know it's kind of a shape, an irregular shape that shows some stuff. So now, if you remember what we saw in the nearest neighbor previously, it says that the nearest neighbor first starts by assigning what? Some function, right? To a value of the instance. Yes? Where we saw a function f of x, and we saw some instance x of I, yes, which is a training instance, which is nearest to a new instance that is to be classified s of q, and whose value, the largest value, is k, yes. Then the algorithm first finds the what? Most common value among the k nearest examples. Now, an illustration of this would be a situation where we have some points to be classified in a plane. So we take your classical example, which we have. Why don't we draw it now? We have some points. So the points will look like this. So illustrative example. We have this, and we have that, yes? Okay, let's say we have to classify whether this point belongs to the positive or the negative instance. So which point now? First of all, let's have some instances. Negative, negative, positive, negative, negative, right? So the concept here is I have 4 negatives in there, in this circle, and I have, okay, let me keep the positive here. I have negative there, okay? Now look here. If I have a new point which is to be classified SQ, which is this dot, okay, SQ is that dot. Now let me bring it closer. So to which instance will it be classified? So when I choose the nearest neighbor to be one nearest neighbor is going to classify it as positive. But please remember what I told you previously. It's not a contradiction. If I look at this and go by majority voting, it will classify it to what? Negative, right? Because if you count here, only 1 positive is there, 4 negatives are there. So this will belong to the negative instance, no doubt, or negative class now. So the new instance, which is SQ, which is to be classified, if I choose one nearest neighbor, and it makes sense that this is closest to what? X, to positive. Choosing one nearest neighbor, okay, using, let me not say choosing, let's say using one, n equal 1, comma, nearest neighbor, comma, xq will be assigned to what? Positive instance, positive class. No doubt. Now when I change this nearest neighbor to be 5, okay, xq will be assigned to what? The negative class. I hope that made sense. So, now these query points outside the polyhedron are also what? Closer to some training examples. And this kind of diagram is called what? The Voronoi diagram of the sets of this example. Now, how do we represent this Voronoi diagram? With n equal 1, the Voronoi diagram will look like this. Diagram. This is the diagram of the instance space, aka instance space diagram, okay? Aka instance space diagram. Is equivalent to, will look like this. Now, we are talking of n equal 1, right? So we can put a bounding box behind it, something like this, right? And this is the instance to be classified. Are you with me? Yes? So this is the instance to be classified. Now, after this instance, there are other instances that surround this, right? How many instances are there? 1, 2, 3, 4, right? So we can have here, it doesn't matter, shape. 1, 2, 3, and 4. Okay? So here I have some points. 1, 2, 3, and 4. Are you with me? So this is the Voronoi diagram. So this is for one instance. And with this, we will look into what? The KNN for continuous valued function. We saw KNN for discrete valued function, right? Yes? So we are looking into next one will be what? KNN for continuous valued function. All right? That KNN can also be used in approximating continuous valued targets, continuous valued functions, because we can actually calculate the mean of the training examples rather than calculating the most common value, which was what happened in what? Discrete valued function. Now, we can actually approximate this real target valued function by replacing the argmax function with what? K. Such that the formula will look like this. Remember, in discrete valued function, we saw f of x. So in continuous valued function, we call it f hat of x, no problem, which is a different one. Now, we are going to approximate this, right? We remember we saw argmax of some function. That argmax, we are going to replace it with k, yes? Because when we say mean, remember, mean means what? I'm taking an aggregate, right? So I'm going to divide some function by the aggregate k. So I'll get off f of what? Xi, such that this I goes from 1 to k, right? So this is what we'll have when we look into what? The real discrete valued function, okay? Now with this, that will lead us to what we call the distance weighted nearest neighbor algorithm. Because if you look at this continuous valued function, in most cases, we calculated the Euclidean distance. So after calculating the Euclidean distance and then dividing it by the mean, why don't we weight this? Usually we weight this to normalize the values, okay? So if you remember somehow in your neural network class, we try to normalize the value so that we don't get what? A kind of a very large value as an input or something. So we normalize it and then we use that to make predictions. Because remember, your weighted values, which are the values from your nodes that move from input to the corresponding hidden and output, were usually what? Randomly selected, and they were small, right? So in this case now, it's worthwhile to look into discrete weighted nearest neighbor, okay? And that you will see how it's actually similar to your continuous valued function. So that an improvement of your nearest neighbor algorithm is the weight contribution of each of the k nearest neighbor to the distance of that point, that query point which we call SQ, right? So this gives a greater weight to the what? Regions that are closer to it. Because remember, the aim is to make the distance between the class very small and within the class very small and outside the class very large. So within, we call it intra, and outside, we call it inter, different classes. So for instance, if you remember the algorithm which approximates the discrete value target functions, each neighbor was weighted according to the what? Inverse square of its distance from that point. And this can be accomplished by replacing the final line of that algorithm by what? We will write the same algorithm again, and then we will replace it by, we said inverse square. That was all we saw, right? But, in this case now, we are going to include what we call what? The weighted what? Value. So that weighted value will look like what now? Wi. Yes. And with this Wi, this becomes updated, and we have what? The weighted distance, which we call f hat. Yes? Fine. So this is it. But what is this now? This is inverse square, right? So we have to define this. Where Wi is inverse square, right, of what? The distance. So what was the distance? The distance of what? XQ with what? X. What was that? The point to be queried. That's what we said with this. And we squared that. Yes? So this is what we saw. Right? And this is the new weight. So I can also extend this to what? The real value target function by replacing what? The final line of this algorithm with what? Which final line am I talking of now? Which final line? By replacing or by introducing another concept. What is that concept now? Now watch here. The final line is this one, right? So for no argmax, f of what? This is the updated value. F of what? X of q for real value will be what? Quickly. Same summation of as I goes from 1 to k. Yes? Now what did we get? We introduced the weight with what? F of what? Xi. Yes? So we introduce the weight with f of what? Xi. Now we divide it by what? Wi. Yes? That is the weight. So we divide this by Wi. But not only Wi, yes? Again, it's a summation of that. Fine. So this is how the weighted relationship for real value is different from discrete value. That leads us to the next thing. Now that we have seen some algorithms, I've seen algorithms of KNN and some concepts, and we are able to calculate the distance, weighted measure, and some stuff. Why don't we talk about the advantages and disadvantages? So that leads us to advantages and disadvantages. So first we say highly effective. Robust to noisy data. Robust to noisy data. This is noisy in the sense if you are talking about class marks or scores of a student in an exam. Nobody is permitted to get beyond 0. Minimum a student can score is 0. Just imagine mistakenly someone entered -90 in place of 90. This approach of smoothing out will help us to eliminate that, right? By taking absolute value of that and then dividing it by a threshold. And now you see that actually weighted nearest neighbor is the practical solution when we deal with what? Problems in classification and regression. Okay? Now, and what are the issues now? The first challenge here is what we call cost of dimensionality. And next is indexing. So two issues or two challenges here. Practical issues with KNN. Issues with KNN. I hope you can see the board. Practical issues with KNN, and I will explain this in detail. One is curse of dimensionality. And second one is what? Indexing. Problem with indexing. All right?